Swayam Prabha. Digital India. Educated India.
Welcome back, students, to this lecture. Last time we left off by finishing the classification of different type of slopes: mild slope, steep slope, critical slope, horizontal bud and adverse slope. All right, and now we are going to solve some questions. Couple of problems on this topic. So, the question is, find the rate of change of depth of water in a rectangular channel which is 10 meter wide and 1.5 meter deep when the water is flowing with a velocity of 1 meters per second. Okay? So, the channel is 10 meter wide and 1.5 meter deep, and the velocity of the water that is flowing is 1 meters per second. The flow of water through the channel of bed slope 1 in 4000 is regulated in such a way that the energy line is having a slope of 0.00004. See, we have been given S naught, we have been given SF and other things, the velocity. Okay, and so what we have to find the rate of change of depth of water. So, we have been asked to calculate dy by dx. All right. So, now you understand, most of the other things are given very, in the last lecture what we have studied, we are going to use that. So, best is to go to the whiteboard. Okay. So, okay, we are going to see the solution. So, what things we have already been given is B is given as 10 meter, depth we have been given 1.5 meter. All right. We also have been given velocity of the flow 1 meters per second. Bed slope also has been mentioned 1 in 4000. So, 1 by 4000 is the bed slope. We also have been given the slope of SF is also given, that is 0.00004. All right. So, this is quite a simple thing. First, what we need to do, we need to calculate the area of the flow, and that is nothing but B into Y. So, 10 into 1.5, and that is going to be 15 meter square. All right. So, we will go very systematically. T is the top width is nothing, top width is B, that is 10 meter. All right. Discharge is area into velocity, correct. Area is 15 meter into velocity is 1 meters per second. So, that is 15 meter cube per second. So, we have been given Y, we have been given B, we have been given we have been given V, S and SF. So, we calculated A as 15 meter square, top width is anyways given already 10 meter, and Q is we calculated 15 meters cube per second. So, what is the equation in the gradually varied flow or in any type of flow that we have derived? We have derived that dy by dx, this is the equation that relates dy by dx to the some number. So, we have been asked to calculate dy by ds. So, this is the thing that we need to find, and the equation was dy by dx is equal to S naught minus S f divided by 1 minus q square multiplied by t divided by g into a cube. All right. So, dy by dx is going to be S naught is 1 by 4000, okay. SF is 0.0004, all right. Yes. So, 1 minus q is 15, all right. So, it will be 15 square into t is 10 divided by g if we is 9.8, all right, and then a cube, area is also 15. So, 15 cube, all right. So, if you calculate that, dy by dx will come out to be 2.25 into 10 to the power minus 4. Will this have any unit? No unit. So, if you see the slope dy by dx is very small, right, we can say much less than 1, true. So, this is in fact, okay. So, I will write here, this is in fact a gradually varied flow, all right. Good. So, we go back, see this is so dy by dx came out to be, sorry, (2.25) into 10 to the power minus 4, all right. So, okay, I will erase this, and I have included the solution here as well. So, that same thing, these were the things that were given, area, the same thing which we have worked out in the screen. So, the same formula dy by dx is equal to S naught minus SF, and this is what we are going to get, all right. So, this was the final answer which we have seen on the white screen, okay. So, now we are going to look at another problem. So, the question is a rectangular channel with a bottom width of 4 meter and a bottom slope of 0.0008 has a discharge of 1.5 meters cube per second. In a gradually varied flow in this channel, the depth at certain location is found to be 0.30 meter. Assuming the Manning's n is equal to 0.016, determine the type of gradually varied profile. So, see, we have been given the bottom width 4 meter, right here, all right. Slope S naught is given, Q has also been given, and we have been given Y as well, okay. Manning's number is given. So, what type of the gradually varied profile will it be? So, that we are going to see, and it will be a very good practice for you when you start applying the things that you have learned in this particular question about the mild slope, steep slope and adverse slope, critical slope and the horizontal bed. So, as I will go to the white screen. So, to start, this SOLN means solution. So, what are the things that are given to us? so I'll draw. So given is B is equal to 4 meter. Y we have been given as 0.03 meter. Okay, this Y is given. Q has been given as 1.5 meter cube per second. S naught is also given 0.0008 and Manning's roughness is also given 0.016. All right. So now capital Q by B is 1.5 divided by 4 is 0.0375 meter cube per second per meter. So this is small q. All right. So in the normal, I mean, you remember the way we calculated the critical depth, YC was q square by g to the power 1 by 3, if you remember the formula from our lectures last week. All right. So this is going to be 0.0375 whole square by g is 9.81 and whole to the power 1 by 3. If you do this calculation using your calculator or by hand, this is going to be 0.243 meter. So critical depth which we have got is 0.243 meters. All right. What is the other thing that we need to find? So we can use the Manning's equation and see 1 by n A into r to the power 2 by 3 into S naught to the power half. All right. So we see area we already know. All right. Okay. So if in this is a rectangular channel, right. So if this is the y and this is b, so area is b y naught already, because if we also need to calculate the normal depth, right. So area is going to be b y naught. So using this hydraulic radius will be a by p. All right. So here it is actually 4 y naught. So a radius, hydraulic radius will be 4 y naught divided by 4 plus 2 y naught. Okay. So if we use all these value in this equation here, so q is 1.5 given is equal to 1.016 is n, a is 4 into y naught, radius, hydraulic radius is 4 y naught divided by 4 plus 2 y naught, and this whole to the power 2 by 3. All right. And then multiplied by S naught to the power half. S naught is given 0.0008 to the power half. All right. So this will actually give us y naught to the power 2 by 3 divided by 4 plus 2 y naught to the power 2 by 3 is equal to 0.0842. Okay. So if we solve this, you can use any method and we will obtain y naught as 0.426 meter. So the normal depth we have calculated using Manning's equation. All right. Is that true? Because that was the thing that we started with. So, YC came out as 0.243 and the normal depth came out to be 0.426. Now, if you see, we were talking that if there is, you know, if there is a horizontal bed, there is not going to be any normal depth, and see why we were saying that. We were saying that because if S naught is equal to 0, then this Q, there is no existence of Q as such according to this equation. Also, when the slope was adverse, so S naught is less than 0, then this means S naught to the power half is an imaginary number. So, okay. So, concentrating YC is 0.243 and Y naught is 0.426. So, first thing, since normal depth is greater than YC, this is going to be an M slope, right, first of all, M slope channel. Now, the water depth is actually 0. Yes, so actually water depth is not 0.03 which I wrote, it was 0.3 meter here, all right. Okay. So, we see this, the Y naught is greater than Y, and so this is critical depth. This was 0.426, this was 0.3 and this was YC was 0.243. So, which type of curve? This is an M slope, plus since Y lies between Y naught and YC, it is going to be M2 curve. So, this is a good example, a very simple and good example indicating how you have to find the type of the GVF profile, all right. So, this came actually to be M2 curve. I will just erase this. So, this is actually 0.3 meter, because the depth is 0.3 meter. So, this is a typing error, okay. All right. So, all right. So, similarly we have this again a typed solution available. I think I will just correct this one when I provide you with the course material. So, these are the things that were given. So, similarly we have calculated small q and critical depth is calculated like this. You see, this is small q has been calculated the same way, it came out to be 0.243 meter. So, now using the Manning's equation we estimated the normal depth Y naught, and this Y naught came out to be 0.426, all right. Since it is Y naught is greater than YC, it is a mild slope, and Y is greater than Y naught, so it is called an M2 curve. So, we have another question. A wide rectangular channel has a Manning's coefficient of 0.018 for a discharge intensity of 1.5 meters cubed per second per meter. Identify the possible values of gradually varied flow profiles produced in the following break in the grade of the channel. S01 is 0.0004 and S2 is going to be 0.016. Okay. So, this actually is a good question. So, we will, so because in this topic we have less number of questions. So, I think it is better to solve it here, white screen. So, the solution shall go like this. So, discharge intensity is small q is equal to 1.5 meter cube per second per meter. Okay. So, Yc will find by small q square by g to the power 1 by 3, very simple formula, must be remembered actually, by 9.8 to the power 1 by 3, and that is going to be 0.621 meter. All right. So, for normal depth, what do we use? Manning's equation. All right. So, for wide rectangular channel, so it is so wide, so hydraulic radius becomes y naught itself, all right, for a wide rectangular channel. So why you must have a question why. So, hydraulic radius is A by P. So, B y naught is A, P is B plus 2 y naught. If it is wide, that B is very much greater than y, right. So, B plus 2 y naught will more, or because it is very wide. So, this will B plus 2 y naught will be approximately equal to B. So, this B and B gets cancelled, that is why we say normal depth. For normal depth for wide rectangular channel, the radius, the hydraulic radius is normal depth itself. So, now we use this formula, q is equal to 1 by n y naught into y naught to the power 2 by 3 into s naught to the power half. You can also use that formula, capital Q, all right, but I find it by using small q much better. So, we can do, so y naught can be written as n into q divided by under root s naught to the power 3 by 5, all right. So, this implies y naught is going to be, n is, we just substitute in the value 018, small q was given as 1.5 and this under root s naught all right. So, so the question is, so actually we can draw a table here. That says slope and y naught. So, 1, 2, 3 and 4. So, there are 3, there are slopes 0.00, 0.04, 0.016 and then there is a critical slope, all right. Because this is the critical . All right. So, for this S naught, the normal depth if we put, we can get, this is the one part 197 and if you put S naught as 0.016, we are going to get 0.396 and Yc is 0.612, right. There are two normal depths y01 and y02 here. So, one we put 1.197, the other is going to be 0.396. So, this is what is written, all right. So, if you go from 1 to 2, since y naught here, this one is greater than Yc, this is mild slope, first one. But in the second case, the y naught is less than second case, y naught is less than y c. So, basically this is the steep slope. So, the resulting M2 curve on mild slope and S2 curve on steep slope, all right, because the water depth is also, it is here, all right. So, the type of grade change is mild to steep, all right. So, basically until this is fine, okay. Good. So, we have included the solution again here for your convenience. So, now we start with rapidly varied flow, and then it is almost to the end, but we will start with some concept of the rapidly varied flow. So, you see the figure here, and what do you notice? See, if you see, there is something that is coming with a velocity v here, and somehow this height is larger, right. I mean, this seems that there is something which is different from this area. So, the velocity becomes v 2, all right, maybe the height has increased or there is a bump or something. So, in that case the flow becomes, so it varies very rapidly. Suddenly if there is something, the rapid change in the water level elevation or some water level elevation, it is called rapidly varied flow. In this particular case, there is a hydraulic jump due to the change in bottom elevation. We are able to say that because we know it from before. This is the photograph from probably one of the experiments, all right. So, that was a fair introduction to rapidly varied flow. You now understand what hydraulic jump is one type of rapidly varied flow. So, if you see a flow like this, if there is a flow coming in this direction and the area suddenly increases, that is the rapidly varied flow that happens due to the transition. So, first was due to the height, the second one was due to this one is due to the transition. So, changing the area, transitioning from smaller area to larger area, for example. So, now the most famous type of rapidly varied flow is called hydraulic jump, okay. So, this is the concept that becomes the core of our next two lectures, and we will start the next lecture, and with this particular concept hydraulic jump, go through a small derivation and solve some problems which will give you a better understanding of hydraulic jump. So, this is all for now. I will see you in the next lecture. Thank you.